Right, what do I actually need before I start machine learning? I get asked that more than any other question, and most answers online come from one of two camps. One tells you that you need almost nothing. The other tells you that you need calculus, statistics, and 3 years of Python before you're allowed to touch a model. Both are selling you something. The honest answer sits between them, and today I'll give it to you properly, with real hours attached. Here's the shape of it. The list is shorter than the intimidating camp wants you to believe, but it's not as short as the just enthusiasm camp wants you to believe either. There's a real list. By the end of this video, you'll know exactly what's on it, how long it takes, and how you'll know when you're done with each piece. Then we build your whole working setup, browser and local machine both, so you never have to think about this again. I split what you need into 4 tiers. Each has a job, a time budget, and what I call a finish line test, one concrete thing you should be able to do that proves you're ready to move on. Not a feeling of confidence, an actual test. Tier 1 is Python, not all of it, the 20% that machine learning actually touches, which is exactly what Part 3 teaches, drill by drill. Budget 20 to 25 hours if you've never coded before, halve that if you've dabbled in any other language. Your finish line test. Write a function that takes a list of numbers and returns their average, from memory, unaided. That one function uses a definition, a parameter, a loop, or a built-in sum, a division, and a return value. Nearly everything Tier 1 is built from. We come back to that exact function in Part 3. Tier 2 is maths, and hear this properly. You need intuition, not derivation. You need to read maths and know what it's telling you, not produce it on a whiteboard. Budget 10 to 15 hours, and here's the complete list, 6 ideas, not 60. 1. What an average and a spread tell you about a pile of numbers, clustered near the middle or scattered everywhere. 2. Correlation is not causation. Two things moving together doesn't mean one causes the other, probably the single most common reasoning error in data work. 3. What a vector and a matrix actually are. A vector is a row of numbers describing one thing, a matrix is a table of those rows stacked up. 4. A derivative is a rate of change, full stop. 5. Basic probability, how likely something is, as a number between 0 and 1. And 6. The one that surprises people most, why 99% accuracy can be a genuinely terrible result. If 99 borrowers out of 100 never default, a model that lazily predicts never defaults for everyone scores 99% and is completely useless. We prove that with real numbers in Part 5. Your finish line test. Explain standard deviation out loud in one sentence, unaided, something like it tells you how spread out the numbers are around the average. If you can say a sentence in that shape, you've got the intuition, not the formula, the sentence. Tier 3 is tools, roughly 10 hours, and the most mechanical of the 4, which makes it the fastest to tick off. Notebooks, the cell-by-cell way of running code you've already used twice. Pandas, for loading and reshaping tables of data. NumPy, the fast maths underneath almost every library you'll import. Matplotlib, for turning numbers into pictures a human can read. And Git, for saving your work properly instead of a folder called final version, to actually final. No separate finish line test here. Tier 3's test is built into every remaining part of this series, starting with Git in about 10 minutes. Tier 4 is different. Not a syllabus, a set of habits, and it never really finishes. Read the whole error message, not just the last line, before you touch anything. Read the documentation before you go hunting for a tutorial. It's written by the people who built the thing. Use AI tools as a tutor that explains, not a vending machine you paste from unread. Ask it why, not just give me the answer. And keep a project log, a plain text file of what you tried and what happened. Because 6 weeks from now, you won't remember why you made a decision, and future you will thank present you for writing it down. So let's add it up, honestly, out loud. 20 to 25 hours of Python, 10 to 15 of maths intuition, about 10 of tools, and habits that cost nothing extra because you build them while doing the other 3. That's 40 to 60 hours total. At 90 minutes a day, that's about 30 days. 1 month, done properly, at a pace you could keep alongside a job. Not a weekend, and not 3 years either, 30 days, honestly spent, and you're standing at the real starting line. Maths lesson over. Let's build your actual setup, because this is the part almost every course skips, and the part that quietly wastes people the most time. We're doing it properly, both ways, because you genuinely need both for different jobs. First, Colab, which you already touched in part 1. Go to colab.research.google.com, sign in with any Google account, and click New Notebook. That's the entire install process, because there isn't one, nothing downloads to your laptop. Here's what's actually happening, because it saves confusion later. That click hands you a runtime, a real machine sitting in a Google data center with its own processor and memory that you're borrowing for free. Every cell executes over there, not on your laptop. Your laptop's job is displaying a web page and sending keystrokes across the internet. Close the tab, and eventually that borrowed machine gets wiped, which is why anything worth keeping gets saved to drive or downloaded. And if you want a graphics card, a GPU, for the heavier maths later, Colab will lend you one too, free with limits, runtime, then change runtime type. We won't need it until part 7. Now the local install, Python running directly on your own laptop. You'll want this from part 6 onward, building one continuous project with its own folder and history, so let's set it up properly now. Go to python.org, download the installer for your system, and run it. On Windows, there's one checkbox that matters more than every other setting on that screen combined. Add Python to path. Tick it. Skip it. And your computer has Python on the hard drive and genuinely can't find it when you type Python anywhere else. The single most common support question in every beginner course on Earth. On a Mac, it mostly just works. Next, an editor. I recommend Visual Studio Code, free, and what we use on screen for the rest of this series. Install it, open extensions on the left, search Python, and install Microsoft's official one. That gives you syntax highlighting, error checking, and the ability to run notebooks locally inside the same editor. Now, virtual environments and the actual why. Imagine you're a tradesperson with one shared toolbox in a van used on every job. Fine, until one client needs metric spanners and another needs imperial, and jobs start quietly breaking because you're never sure which set is in there this week. A virtual environment is a separate, sealed toolbox per job. Project A gets its own bubble of libraries at whatever versions it needs. Project B gets a different bubble entirely, and the two never interfere. Skip this, and one project's install will eventually break a different project that was working yesterday. Creating one is one line, Python venv. Venv, then you activate it. The command differs by operating system, worth noting in your project log. Once active, anything you install with pip, Python's package installer, goes into that sealed toolbox alone. And with that in place, you run the exact same notebook style you've used in Colab locally against your own machine's hardware instead of Google's borrowed one. Same cells, same shift and enter, your computer doing the work. So which do you use and when? Simple rule. Parts 1 through 4, learning, experimenting, throwaway exploration, stay in Colab, 0 setup, free hardware, nothing to maintain. From part 6 onward, one continuous project with its own history and files that need to persist exactly as left, move local. You'll use both for the rest of your working life. Now Git, and before the commands, the actual point of it, because nobody explains this part. Imagine 3 hours getting a piece of code working. One more small change to try something, and it breaks everything, and you can't remember what you changed or how to get back. Most people's fix is copying the whole folder before every risky change. Final version 2, actually final. A mess that gets worse every week, and that nobody, including its own author, can make sense of 6 months later. Version control solves exactly that properly. Git snapshots your project whenever you tell it to, with a short note on what changed, and lets you step back to any snapshot cleanly, without 17 copies of the same folder lying around. Insurance against your own future mistakes, and it takes about 10 minutes to learn the part you'll use 90% of the time. 3 commands inside your project folder. Git init turns an ordinary folder into a Git repository, a hidden Git folder appears, and from that point Git is watching. Git add followed by a dot stages everything, meaning include these in the next snapshot. Git commit with a short message in quotes saves that snapshot permanently, note attached. Later, once you're pushing to a host like GitHub, Git push sends your saved snapshots up to a server, so your work exists somewhere other than one laptop. One more file worth knowing. Git ignore, a plain text list of files Git should never track, a virtual environment folder, cache files your computer regenerates automatically. Large, machine-specific, and they don't belong in a history you might hand to someone else. Hands on keyboards. Open the Part 2 notebook, Colab or local, it works in both, and the first thing it does is tell you which one you're in. First cell checks whether Google. Colab can be imported, that module only exists inside a Colab runtime, then prints your Python version and operating system. Run it, and read your own report back before moving on. Second cell checks the libraries this course leans on, NumPy, Pandas, Matplotlib, Seaborn, scikit-learn, Sutil, by actually trying to import each one, not guessing. Anything that fails lands on a missing list. Third cell installs only what got flagged. All clear above, and this one prints nothing to do and moves on, the correct outcome, not a failure. Fourth checks hardware, RAM, CPU cores, and whether a graphics card is present, by looking for a tool called NVIDIA SMI rather than assuming one exists. Not detected is completely normal. Everything through Part 6 runs fine without a GPU. Fifth, a habit worth learning cheaply now. A notebook remembers whatever cells you've run, not whatever's written above them on the page. Rerun an earlier cell out of order and its memory can go inconsistent with what's on screen. Feels wrong, restart and run all, top to bottom. Sixth, slow down for this one. A cell broken on purpose, importing NumPy misspelled. Read the traceback bottom up because the last line matters most. Module not found error, no module named NumPy. The class of error always means the same thing. Python looked for a module by exactly this name and couldn't find it anywhere. The text after the colon is the exact misspelled name it searched for, which is where the typo jumps out once you actually read it letter by letter. Spell it correctly, and it imports clean. Seventh, we write 2 files that make this project handable to anyone, future you included. Requirements.txt lists every library the project needs, so someone else, or Colab, can recreate your setup with one command. And git ignore, listing the cache and environment folders Git should never track. And now, in an actual terminal, because Git behaves oddly runs cell by cell, type the 3 commands we just covered, git init, git add. Git commit with a message like initial commit, environment setup. Your first real commit, a habit you repeat after every meaningful chunk of work from here on. Last cell, the checklist. Python installed, environment identified, every library importing cleanly, a real traceback read and fixed, both files written, your 3 git commands known. Every line reading OK means properly, professionally set up, not good enough for now. So what do you own now? 4 tiers with real hours attached instead of vague dread, 20 to 25 for Python, 10 to 15 for maths intuition, about 10 for tools, an ongoing set of habits. A working Colab account, and if you followed along locally too, Python, VS Code, and a virtual environment on your own machine. And Git, not as a scary ritual, 3 commands that save you from your own future mistakes. Homework. 1. Run the Part 2 notebook yourself and get every line of that checklist to say, okay, don't just watch me do it. 2. Make one real Git commit of your own, on any folder, with your own honest message. 3. Write down 1 sentence each, your own answers to the 2 finish line tests so far, averaging a list from memory, explaining standard deviation out loud, even if you can't fully manage them yet. That sentence is how you'll notice your own progress. The notebook's linked below, alongside the written handbook for the whole series, cheat sheets, glossary, and that 30-day plan, laid out day by day. Part 3 is the 20% of Python we've been talking about all video, taught as drills, not lecture, ending on that exact averaging function that's your finish line test. Subscribe so it finds you. And if you'd rather work through all of this as a structured course with graded exercises, the full guided path is on Udemy through CloudNimbus. Everything's linked below. You've got a real setup and a real plan now, not just good intentions. I'm Rohan Singh, this has been CloudNimbus, and I'll see you in part 3.